Okay, today we're going to talk about advanced manufacturing strategies to improve material efficiency, to improve productivity, a lot of different things. These are the performance of your nesting and manufacturing practices here is what we're going to be discussing today. These are some very complex ideas and applications of nesting, and so we're going to go through that in detail today. Okay, first of all, let's talk quickly about nesting history. Nesting history-wise, nesting has been focused on material efficiency, on programming performance, improving programming performance, and machine performance. This has kind of been the historic focuses that nesting has been in. What we're going to do is go well beyond that and to approaching strategies that attack real-world problems. These are sophisticated strategies that we're going to be talking about that can dramatically improve things like the chaos that's on a typical shop floor. Most people have parts that are hot parts that show up unplanned. Machines go down. Operators don't show up. All kinds of things. Schedules change. Just a myriad of unplanned events. And so we're going to be addressing strategies that manage the chaos on the shop floor. We're also going to talk about improved product flow. Typically, in the past, nesting systems have managed order flow very well, but we're going to go beyond order flow into to managing groups of parts in dissimilar materials, such as products or kits or subassemblies, and being able to manage those effectively through multiple machines. So we'll be talking about that capability. Also, we'll be dealing with the scrap issues and remnant issues and eliminating scrap and some strategies that dramatically improve your material efficiencies and eliminate remnants. We'll be talking about dynamically balancing machine load and how that's done with multiple machines of dissimilar capability. Of course, we'll be talking about improving material efficiency through some strategies that avoid what's called tail-off, and we'll get into defining tail-off and understanding what that does in the shop floor. Also, we have some strategies that greatly improve tooling setup. So on your punch presses and other machines that require tool setup, we're going to talk about some strategies there that will accomplish some significant tool setup reduction. And then master kit flow. This is again the flow of parts through your facility in group format. Okay. Now, the old strategies has typically been used for nesting in the past. I'll go through them very quickly. There's been static nesting, and static nesting solves a lot of problems until some of the exceptions show up, and then you have significant problems. Plus, oftentimes static nests don't lend themselves well to material efficiency because of there's just not enough parts to build a single static nest that you know are always going to come together. People have moved to interactive nesting. There's a lot of interactive nesting going on, especially in other products besides Optimation. Problem with interactive nesting is that it's very difficult to keep up with machines in a short time frame. And when the time gets short, a lot of opportunities are missed in terms of getting the right parts at the right place and getting the efficiencies and so on. Batch nesting came in a few years back. Batch nesting solves the time problem because it automates the nesting process, thinks through the problems of nesting parts and so on, and very quickly generates those nests. But batch nesting also has its challenges. Often batch nest plans run several hours or even days in some circumstances. And of course, the chaos on the shop floor comes in and makes that plan obsolete within a short period of time. So batch nesting has its problem with that sort of thing. It also has some significant efficiency issues that we're going to point out as well. So let's kind of go through an example here quickly of what what the problems are with batch nesting, and then how we're going to solve those particular problems. Okay, the nesting engine is creating a batch of nests based on a current set of orders. These current sets of orders, because batch nesting runs rapidly, that during the nesting process, typically the order requirements do not change. So you're able to, as you batch through all of these, you're able to look ahead. Another advantage of batch nesting is to know what the load is on your machines and be able to plan your manpower from that. That's an advantage. But there's a significant disadvantage, and that is that as you nest any single group of parts, as you get toward the end of those parts, you will notice that your material efficiency drops off. And we'll talk to that a little more here in just a minute. In fact, it can get so bad that the last nest can have some very significant material that is unused. And often people want to create a remnant from that because it's so large, it could be used again in another process. So this remnant management becomes an issue with batching as well because of the tail-off issue. And then another group of parts come in and you start the process over again. Now, let me show you here in graph form kind of what we're talking about in this tail-off problem, because this is one of the most expensive parts of batch nesting, and that is that as you make nests, the efficiency begins to get smaller and smaller as fewer and fewer parts are available in that group that you started with. And of course, that creates this tail-off effect, or the drop in efficiency as the nests are built. And that can be a significant cost. Okay, so we're going to talk about strategies here in just a moment. Also, batch order processing reduces your flexibility significantly. For instance, if hot parts show up and you have a plan with that includes 10 or 20 or nests on the floor, it's very difficult to deal with that. There is a way to do it. You can pull those nests back and re-nest them and create a new plan with the hot parts included. But these things happen so quickly with schedule changes and machines going down. And those types of things happen so rapidly that batch order processing has a very significant difficulty responding to those in real time. So that kind of chaos on the shop floor is not something that batch order processing deals with very well. So we're going to talk about how we're going to deal with those. And to do that, I want to introduce a concept called continuous order flow. Okay? Continuous order flow is different than batch flow because we're no longer interested in producing all of the parts at one time in a nest form. Continuous order flow takes the order requirements that are due now and begins to nest those in, let's say, let's consider this as a single nest. Okay, one machine needs a nest and we start to build that nest. The problem can occur, though, that when you build it out of just the current orders or current requirements, current time bucket, there may be an area on the nest that needs to be filled. So we need a system that's smart enough to look ahead or look in other areas, and we'll talk about these strategies, filler part strategies here in just a bit, that will allow it to pull to forward parts that you're going to be making right away anyway, or that have an immediate demand, so that you blend the current requirements with the next requirements here. So that's the concept of continuous order flow. Now let's see how we can implement continuous order flow. Well, before we get there, let's first look at the efficiency changes that occur based on continuous order flow. Continuous order flow is represented by this red line here at the top. The tail-off of batch processing is represented by the blue line. So as you begin to nest, because you're not trying to run to the end of all of your part requirements, your nest efficiency will stay high simply because there's always new parts coming in that can be used to improve that nest as long as you don't try and drive it all the way to conclusion. So this continuous order flow concept can be used in a principle called JIT nesting. Okay? JIT nesting is a concept which allows us to deal with a lot of things. In fact, the benefits of JIT nesting is that you get the parts you need, the ones that are currently needed right now, and you get them in the quantities that you need them in. You never run out of parts in a continuous flow system because you're not going to try and drive the nesting system to get so far ahead that it runs out of parts. You're going to essentially make nests as production requires them. Okay, and we'll demonstrate that here in just a minute. Dynamically balancing machines is also a product of JIT nesting because, again, because we're waiting till demands occur at the machines all get the amount of work that they can handle. Elimination and reduction of remnants occurs simply because we're not driving things to the point where we're doing partial sheets. We're going to be able to manage unplanned events, in fact, respond to any unplanned event within one machine cycle. Okay, so let's take a look at how dynamic nesting works. Okay, in this case, I'm only showing one machine. Later examples will show you multiple machines. Okay, now what happens is the machine requests a nest, and the nesting system automatically generates a nest and delivers it to the machine out of the current requirements. Notice there is no nest operator in JIT nesting, nor is the machine operator doing the nesting. He or she is simply requesting the nest. Okay, so whenever he needs a nest, he simply signals the JIT nesting system to build that nest for him. Another nest is built and delivered. Okay. Now, as all of this is occurring, additional parts are being brought in from the schedule that show up on the schedule. Hot parts might show up. Schedule changes may occur. All of these dynamic events that we have to deal with are going on simultaneous to the machines actually producing the parts. So as the system asks for nests, the additional parts backfill, more parts follow through, and the process continues so that you have a continuous flow of parts and a continuous nesting process going on here. The machines only get nests when they ask for them, when they're ready to run those nests, and so there aren't any queue of nests that are waiting in the way here to become obsolete. Okay, so there's no queue of nests in front of any of the machines. Everything, the system responds within one machine cycle. So if you have multiple machines in the nesting cell, you essentially can have a very, very rapid response. If you have 5 machines, then essentially, on average, you would be down to 1/5 of a machine cycle. You're going to tame the chaos of changing events because you're going to respond to them within that one machine cycle. Okay, so that's the concept of JIT. That's been around a while. Optimation has a lot of customers using JIT. The next concept I want to build upon JIT nesting with the concept of kit nesting. Okay, so now we're getting into some new strategies that that may be completely new to you, whether you're an Optimation customer or not. These strategies involve defining a kit, and a kit can be defined in a number of ways. It could be a product, it could be a sales order, it could be a sub-assembly, or it could be a job from a job shop, a customer ordering things from a particular job shop. What all of these have in common is that they are made up of multiple part orders that are intended to be produced together to complete a particular group of orders, which become a kit or a product or sales order or whatever it is that your terminology might mean. For this presentation's point of view, we're going to call it a kit because that's kind of a generic term, a group of parts that are associated for some purpose or reason. Now, often these kits are made of dissimilar materials. Nesting systems in the past have had trouble with managing kits across multiple materials, and that's one of the things we're going to be talking about here in this concept. So now also many people use MRP, ERP type systems for generating schedule, and what you may not be taking advantage of is that the ERP MRP system has a product definition and is able to handle through its bill of material explosion of that product, and oftentimes has a tag or association with a group of parts on it. For instance, we have a customer that typically gets 10 or 15 orders of sales orders or groups of products a day. Now the problem they get with MRP is that MRP's job is to release orders based on how long it takes to produce a particular part. And so parts that are difficult or time-consuming to produce, it releases earlier. Parts that are easier are released later. But oftentimes there is a large number of parts that get released in the same time frame. Consequently, you can end up with a time bucket of today where you have 10 or 15 orders that MRP has generated. If you just randomly let a nesting system go at those orders, whether they do it JIT or batch or any other method, there won't be any recognition that those orders, that some of those parts should belong together. For instance, let's take an example of 10 sales orders that are all due, parts that include parts that are all due today, and they all have dissimilar materials. If you'd really like to get sales order 1 completed, and then sales order 2 completed, and then sales order 3 completed, the nesting system has to have some new capability that is able to manage kits or groups of parts together, okay? And so whether it comes from MRP or you're a job shop and you're getting orders in from a customer and you want to finish all of the product that the customer has ordered, and there might be 8 or 10 or 100 different products that they ordered at one time. You want to get that done and shipped and invoiced, or if you have sales orders flowing through, or whatever your situation, or if you just want to manage sub-assemblies to the weld department appropriately, or you want to group parts in such a way that they flow together. This is the mechanism. The mechanisms I'm going to be describing will help you there, whether it be MRP or something else. So what do we need to do with this? We need to create a production plan that will give you the finite details of exactly how to produce these parts in sequence together, okay? And we're going to deal with machine assignments. There might be multiple machines that we're going to be controlling in parallel to one another. We're going to deal with material assignments. We're going to deal with cohesion of the orders that belong to the groups, the kits that we're talking about. We want to manage the setup. We need to avoid any excess work in process or delayed flow. In other words, we don't want to have a kit of 10 parts and we produce 7 of them in the morning, and then by the end of the day we add the other 3. We don't want that kit open for that long period of time and a work in process just sitting there taking up space. All of these types of things are what we're talking about. Now, we're going to talk about kit nesting next, and Optimation has a patent pending on this particular process. We think it is unique enough, and this is just really brand new technology. Okay, kit nesting manages groups of parts so that you produce those parts in together, so that they come out and you're not looking for extra parts. You don't have expediters on the floor chasing this and chasing that and trying to find and put things together. You want to create a smooth production flow. In other words, if you wanted to make one product at a time, you could get unit flow out of this and have it literally flow 1 unit at a time if you chose to make your kits defined that way, or sales orders, or whatever it is that you're trying to accomplish with your kitting process. This, of course, is going to reduce work in process. We want to be able to avoid the material efficiency problems by blending kits together. So as we complete kit 1, we want to blend into kit 2 and not have major gaps in material efficiency and get that tail-off problem that would happen if you were just trying to nest these kits by themselves without regard to what comes next. So I want to allow for some advanced filler and tooling strategies, and we're going to talk in more detail about these filler and tooling strategies, and quite frankly, advanced filler and tooling strategies, both of those strategies are useful in virtually any kind of nesting strategy. So it's not just working within the kit nesting, but we're going to be using these strategies within the kit nesting as well. Okay, now we're also going to marry our JIT capability with kitting, which allows us to inherit everything that JIT gives us: handling of hot parts and schedule changes, dynamically balancing machines, multiple JIT kit cells so that we can manage things like the dedicated tooling in one of the cells and dynamic tooling in another, filler part strategies between cells. All of these things we're going to be able to inherit from the JIT technology. Okay, so let's kind of get our head around this JIT kit nesting concept here and what's going on with it. Okay, first of all, kits can be virtually anything. It can be groups of parts that come out of your MRP system that have a tagged value in an order field so that we know they belong together. It can be any kind of kit order you want to define, any group of kits, sub-assemblies, things of that nature. It could be sales orders for those of you that generate product based on sales orders. And finally, if you're a job shop, it could be literally the jobs you take on and based on the schedule that you want to produce those jobs. So there's a lot of flexibility, and essentially almost everyone, in fact, it's difficult to imagine a manufacturer who doesn't have some sort of product structure or order structure that has a group of parts with dissimilar materials that need to be produced together. So kitting is very universal in the industry, and so let's look at how kit nesting works, okay? Kit nesting works with a number of machines. As any number of machines that you have can be in one or multiple cells, okay? And the process is fairly simple. You make material assignments to those machines. And so in order to, for instance, in the punch press world, to avoid a lot of die clearance changes, you'll make material assignments that have matching die clearance requirements. Those material assignments can be anything you want them to be, though. They can be unique to one machine, or they can be shared by multiple machines. So the material assignments are up to you as to how you want to dedicate the material usage on each machine, okay? But you can limit the number of materials to the machine, and that helps limit the congestion at that machine. So when the nest, or when a machine asks for a nest, remember now these nests are being built automatically. So the machine operator says, send me another nest, okay? And when that happens, the first kit is exploded into its component parts and a nest is generated, okay, based on that kit's requirements. When the next machine asks for a nest, you might find that we will not be able to make a full nest, that there's too much scrap on this nest, too little material efficiency. There is we're going to explode the next kit and add some of those parts to fill out the nest and send it on to the machine, blending the end of the primary kit, the one we must complete, with the next kit, the filler kit. Okay, so the concept of a dynamic filler kit is presented here as one that the second kit will never override the primary kit. The primary kit will always be the one that's most important. As we produce all of the primary kit, well, first of all, before we get to that, we can also limit the number of kits on the output side of the machine. You can see that most of these machines have 3 kits. This machine's limited to 2. This also allows you to manage the congestion on the output side of the machine and make it simple for the operator to be able to segregate by kit and to manage your flow out of the nesting machines as well. As we finish the primary kit, the filler kit gets promoted to become the primary kit, and the process just continues from there. And in fact, you can allow more kits to be open simultaneously. So you can set a maximum limit of open kits. We have a customer that's using this in initial form, or has been using it for a while now, and they allow 3 kits simultaneously open, and in fact find that that's pretty optimal for them. Okay, so that's how JIT kit nesting works. The next thing I want to talk about is the filler strategy concept. You saw at least one concept of a filler strategy of backfilling with next kits and maintaining a flow based on that. We want to continue expanding on these filler strategies. These filler strategies, though, go beyond just JIT or kit nesting and can be used in virtually any of your nesting environments that you strategies that you use. Okay. First of all, let's introduce the concept of hard-to-nest parts. Hard-to-nest parts are parts like you see here on the screen that have a large open area that need companion parts in order to fill up that wasted space. Also, hard-to-nest parts could be just very irregular shaped parts that are complex, that are difficult to nest, and need companion parts to improve their the areas that it's using in the irregular area. Or it could be a very simple part, some very regular part, some kind of mundane part, but that part, when you put multiples on it, just doesn't fit the sheet well. It leaves a lot of space at the top or right-hand side of the sheet, and that just it doesn't fill up, and it needs companion parts to do that. We have tools to be able to examine your nesting history and find these hard-to-nest parts. Okay, those tools we can help you with, help you find and identify where those parts are. The trick is to have the companion parts and the hard-to-nest parts show up in the same time frame. And of course, you cannot predict that in any kind of ordering system because you have no idea what's going to be ordered next. So nesting filler strategies begin to address that by creating a filler part library. Okay? A filler part library is a group of parts that we've identified that are great companion parts that we're willing to time displace. Now remember, the definition of a filler part is a part that will be cut out of scrap. Okay? So you have to adjust your thinking here a little bit to recognize that while we might time displace or advance the production of a filler part, it's only going to be cut out of scrap, so it pays for itself in material what we do with it in terms of advancing the schedule. So these are like order point parts where your inventory system would have a maximum quantity of maybe 100, and then every time it gets down to 10, it reorders another 90 and builds the inventory back up. But only as you have an opportunity to make those parts out of scrap from your other nesting process. So they become companions to hard-to-nest parts that essentially build these out of scrap. And again, we can help you define what these parts are that would be great fillers for the hard-to-nest parts. So once you know the hard-to-nest parts, you know what types of parts you're looking for to assist in your nesting process. There's also an array of logical filler options. By logical filler options, these are options that may or may not be permanent fillers. In the filler part library, they're there as fillers, and these parts are always going to be made out of scrap, and you're always going to be producing them at very low cost because it's the material you would have been throwing away otherwise. In the case of logical fillers, there's a variety of things. One of the tricks that can be used is if you're doing kit nesting and you have kits and you know that these parts are particularly that all of the parts belong to this kit. You can, in fact, redefine your kit and allow some of those parts that are really good fillers that you use a lot of, brackets or whatever they may be that are common parts for you. And you might want to take them out of the kit definition and move them to the filler part library definition. Okay? And so in doing so, that allows you to have a population of part, again, that you're going to time displace so that when the kit comes and needs to be made, you just pull those parts that are pre-made out of inventory to finish your kit. Also, a lot of people use Kanban processes to order their parts. Kanban is a method where orders show up randomly, and you can, again, select and identify Kanban orders as filler parts so that they remain filler parts for some period of time. Let's say typically you have a period of time to build Kanban parts. So let's say you have 2 days to do that. The first day you may want them to be in filler part status. The second day you might allow them or may require them to be built and completed. So they can move back and forth across this definition of filler parts based on their temporary, their current definition of what's required. Same thing can happen with future parts. You can have parts due today, you can have parts due tomorrow, giving the system the ability to look ahead and temporarily say, okay, within a short window into the future, I will allow you to build, to use these parts if you can make them out of scrap. Again, the benefit is scrap, the scrap cost that the part would hold. Alternative materials is also another logical filler. This is a very useful one. Oftentimes, parts are made out of a specific material, but you could just as easily make it out of another material, and it would be acceptable from a design point of view to make it out of another material. A favorite one that we run into fairly frequently is stainless steel, where a customer will have brushed stainless steel for all of the parts that are on the exterior of the product, and then they'll use just standard finish for the parts that are inside and out of view. Well, you can take that standard finish part and say, okay, you can make it out of the standard finish, or if you're nesting your brushed stainless and there's some material I'm going to throw away, go ahead and make this part out of the brushed stainless because it'll work just as well as brushed stainless, and everything will work just fine. So alternative materials is another nuance of how to find fillers and to match up opportunities to make better nests. Okay. All right, that's our advanced filler strategy. Let's go on into advanced tooling strategies. Advanced tooling strategies are quite useful strategies as well. It's common in history to have the concept of a preferred turret or a fixed turret tool load that's in a particular, the tools are fixed in that particular turret and not changed. What we found in one customer's case is that 65% of their product used exactly the same tools, and they would fit within a 58 station turret. Okay? So in tooling strategies, we took a look at the parts and or kits that they had to produce, and we found that there was a lot of commonality of tooling. If we then made 2 JIT kit cells, is what we did for this particular customer, we were able to establish some dedicated machines, that is, machines with dedicated tooling that would never change, and we flow the parts that need those dedicated tooling through those machines. Then we have a second cell that has dynamic tool changing. Those dynamic machines would handle all of the other 35% of their production. So their throughput went way up. They were able to, instead of having a day or more of time, 8 or 9 hours to process parts or kit through a particular facility, it dropped down to an hour or 2. So dramatic improvements in throughput. Their setup time disappeared on the dedicated machines, which was 65% of production. So if you look at your production and you find that there is a lot of parts or kits that have exactly the same tooling, we can set up these dynamic and dedicated machine processes here and make this work for you to improve your throughput of your most common parts. So the way we do that is we run multiple JIT or JIT kit cells. Of course, this can be used with other types of nesting. It requires more attention, but it can be done with other nesting strategies besides JIT strategies as well. Okay. All right. So just to conclude the presentation, got started a little late, and we're certainly run our 30 minutes. So to conclude that, I want to talk about just the final benefits. We're going to get cohesive flow of parts to downstream operation using kitting technology. We're going to get higher material efficiency using continuous flow and nesting filler strategies. We're going to respond to all of the changes in your environment and all the situations that are going to come up within a single machine cycle. We're going to reduce setup using our tooling strategies. We're going to dynamically balance your machine loading. We're going to eliminate remnant through these strategies. And frankly, overall, we're going to improve productivity and lower costs using these particular strategies. Okay, well, that concludes the presentation. I'm going to turn it over to Beth to close us out here and on the presentation portion, and then we'll go from there.